Okay, Kang, thanks very much for accepting the invitation. We're very happy to have you. So please, you can start anytime.
Okay, so thank you for introduction. And also, first of all, I want to thank Blaga for invitation. It's my pleasure to give a talk here. As you see, I will talk about the ghost projection and the expanderish graphs. So Blaga told me this is like a general audience, so I try to make a talk is easy, but now I see there are several experts here, so I think they will feel very boring. I'm so sorry for that, but let's continue. So yeah, I will talk about ghost projection and expanderish graphs. So first of all, I want to explain what is a ghost. So let X be a discrete set. So we could consider L2 summable function, which is a Hilbert space. And then we look at a boundary operator T. Then we can write T as an X by X matrix, where matrix coefficient is a Tx comma Y, which can be written as the inner product of T delta Y comma delta X, where delta X delta Y are orthonormal, canonical orthonormal basis for the Hilbert space L2 of X. Okay, so this is the operator. You can always consider as a X by X matrix. So a ghost is introduced by Guoliang, and so we say operator T is the ghost is that if for every epsilon you can find the final set such that X and Y is outside this final set F, then the matrix coefficient's absolute value is smaller than epsilon. So in other words, T is a ghost if only if the matrix coefficient goes to 0 as X and Y goes to infinity. Here I mean in any direction. Okay, so first of all, we could check that all compact operator are ghost. For instance, you can check all final rank operator are ghost, then you show ghost from a closed set, then you can go to the closure, which is a compact operator. However, the converse is not true. For instance, there exists a block diagonal ghost T, such as T star are not ghost. So in particular, T cannot be a compact, otherwise T star are compact, which is also ghost. Also, we notice that the ghost doesn't form an idea in general because T star is not a ghost. For instance, you can look at this operator. So clearly, this is a ghost because the matrix coefficient goes to 0 in any direction. But the T star is a diagonal operator such that the diagonal contains 1, eventually contains 1. So this is not a ghost, also not a compact. Okay, the problem is that we can find a ghost which is not compact because this matrix block, the sizes, they're increasing to infinity. Once you can control the size of the block diagonal, block matrix, then you can show that all ghosts are compact. More precisely, I mean, if all ghost operators with finite propagation are compact. Okay, to make propagation precise, we need this set X. We cubed a metric has the bounded geometry in the sense that for every R is radius R, and for every ball with radius R has a bounded Catenary energy independent of which center X you have. Okay, so in particular, every metric space with bounded geometry must be countable and discrete. Now we can give one easy examples. For instance, to look at the finally generated groups with water metric with respect to any final generating sets. This is a metric space with a bounded geometry. Okay, if we have a metric, we can talk about the final propagation. So take a bounded operator. We can always find the constant R such that the matrix coefficient is equal to 0 whenever X, Y's distance bigger than R. So look at this picture that so you can think about this infinite matrix. So we are the matrix coefficient is supported on this area. If outside this area is 0, so you could think about this like a generalization of finally supported function to I don't know, matrix coefficient. It's kind of finally supported. Okay. So now you can check that the bounded operator with final propagation, they form a star algebra. Then you can take the operator norm closure. Then you get a C-star algebra. This C-star algebra we call it the uniform row algebra. of x comma d, we write cu star of x, we drop the metric d. Okay, so this is the C star algebra we want to look at it. And every element inside this algebra can be approximated in operator norm by an operator with final propagation, in the sense that they supported the metric coefficient support on this area, and these are outside. Okay, so now we look at the ghost operator inside the uniform row algebra. Instead of look at operator, the ghost operator inside the BL2 of x. In this case, is different. Before we know this is not ideal, but if we restrict our attention to uniform row algebra, then ghost form a closed two-sided idea. So these are the first differences. Then we have the following inclusions. The compact operator are ghost. Ghost operator belongs to uniform row algebra by definition, and by definition is a C star algebra, subalgebra of BF2 of x. So what we are interested in is that when this inclusion is identity. So it looks like a very close to be identity in general, because that I told you that every ghost operator with final propagation are already compact. To prove this fact, you can using final propagation together with the bounded geometry to compute the operator norm. Then you can say this is bounded above by up to some constant bounded by the supremum of the matrix coefficient. Using this fact, you can show every final propagation ghost are compact. So using this fact and the operator inside the uniform row algebra can be approximated by operator with final propagation, you may guess that this is always identity, but in fact it's not. This is a result due to John Rowe and Rufus from 2014. Yeah. So if X is a metric space with bounded geometry, they proved that if ghost operator, all the ghost operator are compact if only if X has a use property A. So I want to explain a little bit what use property A. So A stands for amenability. If you know amenability for a discrete group, one way to define it is that to say that you can find the nets of nets on G, which is the finally supported positive definite function on G, such that the phi I converges to 1 pointwise. Okay, so now you can define the function Ki on the product of G. Instead of G, now it's the product of G. Now you're using the group structure, look at X inverse of Y, then you apply phi I. So now you can use this Ki to say what is the property A of the group G. So you translate the phi I's property, finally supported positive definite, pointwise convergent to Ki. That is the one way to say the group has property A. I will write down the definition of property A, but I just tell you the intuition how property A comes from, the amenability, and coming in this way. So in particular, amenable group have property A, but there are a lot of non-amenable group also have property A, like linear groups, water hyperbolic groups, and so on. If we only interest on the groups when they have property A, then this can be shown that the property A and the exactness, they are equivalent. You may don't know what the exactness for a group. For instance, you can say the group system, reduced group C star algebra is the exact C star algebra. This property is well studied for many years, and in fact, almost every group has these properties, except one kind of group is called Gormaz group. This is the only known example of non-exact groups. So what I want to say is that property A for groups is equivalent to exactness, and this property is everywhere. It's a well-known fact. It's well-known properties. Okay. Okay. So as I promised, I will give a definition of property A, which is introduced by Guoliang Yu. We say that X, comma D has a property A. If you can find R and the epsilon positive number, you can find the S, such and the positive definite kernel K on the product of X, such that if distance of X and Y bigger than S, then kernel is trivial, is equal to 0. If distance is less than or equal to r, then kernel is close to 1 within the epsilon. So let me explain what is a kernel to be a positive definite. So using this kernel, because on the product, you can write kx comma y as your matrix coefficient. Then you get a matrix. Then you restrict this matrix to any finite set. Then you get a finite matrix. Then you say K is a positive definite if this finite matrix is a positive, or someone also say is non-negative or negative definite matrix. Okay, depend your terminology, but what I mean is the positive in the sense of C-star algebra. Okay, so now I want to explain how property A implies every ghost operator are compact. So idea is that using property A, so you can find, so now you choose R to be N and epsilon to be 1 over N. So you can find the sequence of Xn and the positive definite kernel Kn, where Kn x comma y minus 1 is less than 1 over N if distance less than or equal to N, and they are trivial if distance bigger than Sn. So now we look at the Schur multiply coming from Kn, defined on the bounded operator of L2 of x. So how they defined it? So every bounded operator on L2 of x can be written as an infinite matrix, not necessarily infinite, but write as a matrix. Then the Schur multiply given by that what should I say, point-wise multiplication on each matrix coefficient. So this is a definition. This can be shown that when the kernel is a positive definite, you can show this map is a continuous, is a bounded. Then you can translate the property of Kn close to 1, and Kn is equal to 0 if distance is bigger than Sn, to the fact that mknt converts to t in norm for every operator, and mknt has a final propagation. Yeah, final propagation is very easy to see because Kn is equal to 0 if distance bigger than Sn. So propagation is less than or equal to Sn. Okay, using this fact, then we can pick any ghost we want to show is compact. So what we do is that we take the mknh. Then you can easily see that the this operator is a ghost because when tx comma y converts to 0 and the kernel is bounded, of course the product is goes to 0. So mknh is a ghost, but it's also final propagation. So I mentioned it before, final propagation ghosts are compact. Then we also know h can be write the normal limit of mknh, where mknh is compact. So normal limit of compact operator, of course, is compact. That's why we can conclude all the ghosts are compact for property A space. Okay, the converse is a bit involved. This is due to a fact by John Rowe and Rufus. What they did is that they assume the metric space doesn't have property A. Then they construct a non-compact ghost operator inside the uniform row algebra. And the construction is a little bit involved. I will not go to the details. These are like a kind of asymptotically or locally spectral gap argument. Then using functional calculus is quite involved. I will not go to that direction. But then instead, I want to tell you why I want to study ghost projections, as I studied in the title, because there's something to do with the Correspondcon conjecture. So I have no time to explain a lot about this conjecture, but this conjecture claims that there are certain coarse assembly map between the K-series of the uniform row algebra or row algebra, depend your, there may several versions of this conjecture. Claims this map is isomorphism. The point of this conjecture is to tell you that if you want to compute the K-series of the right-hand side, then it's sufficient to consider the conjecture of the left-hand side of this conjecture. And in general, to compute the K-series of the right-hand side of a some C-star algebra is difficult. But the left-hand side is some spaces with nice properties. Then they have a lot of machinery in algebraic topology, whatever you can use. and you easier to compute. For instance, you have like a Murray-Victoria sequences. So this conjecture provide a way to compute the K-theory of the uniform row algebra or row algebra. Okay, so for instance, if space has property A, you can show this coarse assembly map is isomorphism. In general, if X is a coarse embedding into Hilbert space, this also can be shown by Guoliang Yu that this map is also isomorphism. But then we're also interested on the cases where this is not isomorphism. So this conjecture is not conjecture that contains, what should I say, contains the counterexample. For instance, it's shown by many people, like Hickson and Guoliang Yu and Rufus and so on. They proved that the non-compact ghost projection inside uniform row algebra are sources to be the counterexample to this conjecture. More precisely, such projection is not inside the image of a coarse assembly map. But for that, you need a little bit extra condition. For instance, you need, for instance, a space to be a sparser, in the sense that you can decompose your space X to be a disjoint union of non-empty finite sets, such that the cardinality goes to infinity, and the distance between different components of Xn and Xm, they goes to infinity. That's what we say is sparser, because distance increasing between the different components. Okay, so I already gave you a projection, give you an operator which is non-compact ghost, but I haven't given you any non-compact ghost projection. So now I give you one, is called the average projection. This is like is very easy, very easy one. This can be write the block diagonal operator, and each block is a rank 1 projection. And in fact, this projection for each n, the projection is like very easy to define it. So every matrix coefficient is a constant is equal to 1 over cardinality of Xn. So then you can see Pn is a rank 1 projection. Then this is infinite rank projection. So then cannot be compact. And on the other hand, the matrix coefficient goes to 0 because they're equal to 1 over cardinality of Xn, and the cardinality of Xn goes to infinity. So this gives us a non-compact ghost projection inside the boundary operator on L2 of X. But however, to get the counterexample to Correspondcon, we need the projection inside the uniform row algebra. So the question is that when this operator is inside the uniform row algebra, so X cannot be have property A, because we already see that the property A space, all ghost operator in the uniform row algebra must be compact, but P is non-compact ghost inside the uniform row algebra. Okay. In fact, is a well-known fact that if you have a sparse space with this decomposition, and if Xn are expanded, then we can show P is inside the uniform row algebra. Okay, let me okay. So what I said that because it showed all ghost showed that all ghost operator non-compact ghost projection inside the uniform row algebra are counterexample to the surjectivity assembly map. So Correspondcon conjecture fails for expanders. So what is expander? Definition is the following: Xn are a sequence of finite space is expander if there exists a C, and for every n and every subset A, which has some cardinality control. So cardinality of A is at the most half of the cardinality of Xn. Then we have this boundary condition. The boundary of A, so cardinality bigger than C times cardinality of A. The boundary here, we talk about the outer boundary or outer one boundary here. So it's the point inside Xn, but not inside A. But with distance between A is at the most 1. Okay, if you study immutability or of groups or metric space, you may know some condition called the Furner set. C Furner set means that the cardinality of delta A is less than or equal to C times cardinality of A. So expander just tells us that for some subsets with a cardinality control, this set is not C-Funa for the uniform C. So this is a kind of a local negation of Funa sets or amenability. Okay, this is the definition of expander. So let me tell you that the expander exists. In fact, the first concrete construction is due to Margulis using constant probability groups. I will come back to this construction and these examples, but I just let you know that the expander exists, so we can just use it. Okay, so let me short introduce some fact, a little bit about the standard random walks. For that, you can, for each n, you can consider an operator. It's called the Laplace operator delta n, which is a boundary operator on L2 of xn, defined by this formula. A little bit involved, and I don't want to go to details to explain the formulas, but let me tell you what property we know is a bounded operator, and is in fact bounded by 2, and this is the positive operator, and has a final propagation. This is just easy fact to compute it. And there another one is more important, is that the zero eigenvectors are constant functions on xn. For that, to prove this, I mean, there are several arguments, but there are some standard random walks involved here to prove this fact. It's not super hard, but then you need this technique, so this what should I say? This theory of random walks to reach this fact. Okay. There are another characterization of expanders due to Allen and Millerman, that if xn are expanded, if only if the Laplace operator spectrum has a spectral gap at 0 uniformly independent of n. Once we have this, we know all of this fact, it's quite easy to conclude that the expander implies average projection inside the uniform row algebra. As follows, you take direct sum of delta n, is quite you write as a delta. Then, because I told you that delta has a final propagation, so big delta is inside the uniform row algebra because the boundary operator with final propagation. Now we look at the spectral projection, so it's a Katholieke function, Borel continuous Borel functional calculus. But as we see, we have spectral gap at 0. So it turns out this function, Katholieke function at 0, is a continuous on the spectrum. So it's a continuous functional calculus. So they're inside the uniform row algebra. Then you, using the fact that the zero eigenvector are constant function on xn, then you can show the spectral projection is exactly equal to the average projection. It's very simple computation once you know this. Okay, so what I explained is that the expander graphs implies the average average projection inside the uniform row algebra. However, the converse is not true in general. So let me give you an example where average projection inside the uniform row algebra, but xn are not expanded. So this is something called a perturbed expander due to chain 1. In fact, it's really easy construction. You take YMB expander and ZMB any final graphs such that the cardinality quotient goes to 0. Okay, then you construct a new graphs. Just take a union of all of these two. Then you pick any 2 points. Then you connect them by one edge. Okay, this is really easy. Then I claim that the average projection with respect to x is inside the uniform row algebra. Why? You can check that the average projection of x minus average projection on y is the differences is compact. Then you just using this the quotient goes to 0. Then you can see this is a compact. Then compact operator always belongs to uniform row algebra. But the Yn are also expanded, so average projection Py is also inside the uniform row algebra. So then P is inside the uniform row algebra. So say another way is that the Px and the Py are the same up to compact perturbation. That's the reason that Px is inside the uniform row algebra. However, if you like Zn goes to infinity, then you can show easily to see that Xn are not expander. The reason is that Zn form a Fourier sequences with the control of the cardinality. So expander tell us that for the sets with a controlled cardinality is not a Fourier set. So this is the reason Xn is not expanded. Okay. So in fact, it's a long open question that when exactly the average projection P is belong to the uniform row algebra. For that, and we come up with new things. In fact, these things, in fact, I got this idea from Specula. Specula told me this is coming from Rufus. So I should, in fact, I should say this is coming from Rufus. Okay, so this is something called asymptotic expanders. Rufus doesn't give any name of this. He called this expanderish graphs or whatever. And then we come up to this new terminology. So just let you know. Okay, so let's consider a sequence of finite metric space with increasing cardinality. And we say Xn is an asymptotic expander. If for every epsilon between 0 and 1/2, you can find a constant C alpha. So C alpha is dependent on alpha. So this is importance. Such that for every n and every a with the cardinality control. So cardinality at the most half of the cardinality of Xn bigger than alpha multiply cardinality of Xn. Then we have this boundary condition as before. So the only difference between the asymptotic expander and expander is that the C alpha here depend on alpha, but for expander is independent of alpha. So in fact you can let alpha, if C alpha independent of alpha, so you equal to C, always equal to C. So you can let alpha goes to 0, then you come back to the expander condition. So this is the differences of expander and asymptotic expander, whether C depend on alpha or not. So clearly expander implies asymptotic expander. However, the converse is not true. For instance, the perturbed expander that I mentioned in previous slides, I already told you is not expander, but it's quite easy to check this is a asymptotic expander. I will not do that for you, but another interesting question is that can we find another kind of asymptotic expander which is not perturbed expander? We don't want every asymptotic. We don't want to have any asymptotic expander is a perturbed expander. But in fact, this is the case. This is joint work with Vigano and Zhang. We consider a discrete group acting on a probability measurable space with a probability measure and acting in the measure class Persimmon. Using this, look at this probability or measurable dynamic system is able to construct associated graphs using decomposition of the measure and the group translation. You can associate graphs, a sequence of graphs. Then you could show that the associated graphs are asymptotic expander if only if the group action is a strongly ergodic. Okay, and the constructed asymptotic expander in general is not perturbed expanders, is far away from perturbed expander. In fact, I have to mention another result by Vigano before our paper is that they proved that the associated sequence of graphs are expanders if only if the action it has a spectral gap. So expander corresponding to spectral gap action and the asymptotic expander corresponding to strongly ergodic actions. Okay, so I will continue my talk, and I will not go into the proof and the explanation of strong ergodic actions.
Sorry, just a quick question, Kang.
Yeah, of course.
So, just a quick question. So yeah, the example you had before in the previous slide, I forgot. I think you mentioned the name was perturbed expander. So sure, the thing is not an expander, but contains expanders, right? Contains Y. So do you have examples?
Yes, it's a content expander, yes.
So do you have examples of asymptotic expanders which do not contain expanders?
depends your containment. Depends which kind of containment you have. I will explain you that asymptotic expander, not that general, but under some condition, yes. Under some slight condition, yes. So we can show that every asymptotic expander weakly contain the expanders. And under some condition, you can show you can change a weak containment to the coarse containment. You have some nice space, for instance, groups. If you have groups which contain the asymptotic expander, if weakly contained, if only if they are coarsely contained. Okay. So in a way, yes. So in a way, yes. But here is isometrically contained. Okay, in this example.
Thank you.
Yeah. Okay. So let me continue. So using this concept, then we could show that if average projection inside uniform row algebra, then we can conclude Xn are asymptotic expander. So let me say again, in fact, Yang told me that this proof is come from Rufus. So Rufus had this implication. Okay. Okay, I will not, in fact, this proof is not that difficult. And once you can come up with this concept, then everything is quite easier. But to come up with these things, I think it's a little bit tricky. Then later on, we want to prove the converse. Then we made a lot of trouble, and we don't know how to do that. Then we try to ask for help for some people from group series and help us do that. Then we come up idea is that we can try to approximate asymptotic expander by sequence of expander in a good way, and such that you can start the asymptotic expander using the property of expander. This is something we call a structure theorem. So this joint work with Kuho, Vigno, and Zhang. What we can prove is that every asymptotic expander admit a uniform exhaustion by expander graphs. So this uniform exhaustion is a very strong approximation, in particular contains expander in the weak embedding. I don't want to go to details how you define the uniform exhaustion, but I just tell you it's kind of a good approximation. One direction is easy, the difficult one is from left to right. But in fact, the proof is also not difficult in this direction. Idea is the following: you fix k, natural number, then you look at the maximal 1 over k Fuller set inside Xn. Okay, so because I told you that the expander means when you have some sets with a cardinality control, then you want to, it's not a Fuller set. It's not a Fuller set. So now we look at the 1 over k Fuller set. Then we're using the asymptotic expander condition to control the size of a Fuller set. Okay, so we have control of the Fuller set. Now we look at the complement. The complement exactly you exclude the Fuller set. So then you get the expander graphs we call the Y and K. So that's why we get, then you check this set has some nice properties, which is important for us to prove the converse implication. Okay, so this is the roughly idea. So the picture is the following. I mean, for each n, we have some approximation of xn by yn1, yn2, and so on, the increasing. And for each n, you can find a big number mn, depend on n, such that when k is bigger than mn, then y and k is equal to everything. So it's stable from some point. So this is the intuition you should have. Okay, once we have this structure theorem, we can prove the converse of this fact that the Xn are asymptotic expander, then you can conclude the projection is inside the uniform row algebra. So of course, we have to use the structure theorem. So we get a uniform exhaustion of Xn by expander y and k. Then we choose a k, fix the k. Then we look at the disjoint union of y and k. Then we denote by yk, where y and k are expanders. respect to n. Okay, now we can look at the average projection of P, Y, K inside the corresponding uniform row algebra. Why we have it? Because Y and K are expanders. I already told you this happened for expanders. Then because this map is uniform exhaustion, then this gives us a map from uniform row of YK into uniform row of X. Using this map, you can map PYK from this algebra into the uniform row of X. Okay, we look at this image, then we can like K goes to infinity. Then because by this exhaustion, as the picture, the intuition I give you, then the image of PYK inside uniform row algebra normal converging to the average projection of P of X. So this is a very simple idea how to prove this average projection inside the uniform row algebra. Okay. Yeah, what I want to say is that I already told you that all non-compact ghost projection inside uniform row algebra will violate the surjectivity of the coarse assembly map, the Correspondcon conjecture fails. So I have to point out that all the previous known counterexample to the Correspondcon conjecture come from expanders, but now we prove also asymptotic expander give counterexamples. So one of the advantage is that the asymptotic expander is more flexible than expanders. Using this concept, we can construct a lot of new counterexamples. For instance, we can construct uncountably many different family of asymptotic expander. The different means not a coarse equivalent, for instance. And we have uncountably many asymptotic expander, which none of them are expanders. But because this result, they're all counterexample to the Correspondcon conjecture. So this is the yeah.
That's the question about that.
Yeah.
It's not, so as far as I know, unless someone has done something I'm unaware of, just having the ghost projection is not enough to get a counterexample to Correspondcon. You need something else on the space. So
yeah.
Whatever. So
yeah, okay, we can make it to be yeah. I want to, as I said, I want to keep this talk elementary, and then there comes some expert, then tell me that this is some condition missing. Yes, exactly. You need, for instance,
3 words. That's fine.
yeah, the space to be nice. For instance, you want to have a graph which has logicals. In fact, the counterexample we have is a asymptotic expander with the logicals.
They're all large graphs. Okay.
Yeah, for instance, yeah.
That's enough.
Yeah, sorry, I did not make every statement precise.
No, that's good. Thanks. Just wanted to.
But if you know who is my advisor, so you know why I don't want to make everything precise. Okay, sorry. Yes, exactly. You need a little bit more, which I don't explain. I'm just yeah. Okay, so yeah, so this is the main theorem and this is the main corollary. One of the questions we would also want to explain, try to explore, is that when asymptotic expander are expanders. So for that, we can consider some nice graphs. It's called vertex transitive graphs. What does it mean? To give any 2 vertex in your graph, then you can always find a graph automorphism sending X to Y. So what is a graph automorphism? So sending vertex to vertex, send the edges to edges. So in other words, graph automorphism preserves graph structure. So whatever you like, so they preserve. Okay, so let me give you examples of vertex transitive graphs. It's something called box spaces. Yeah, again, I do not do something correctly now. I borrow it. Okay, so you take a gamma, which is the finally generate residually finite groups, where S is the finitely generating sets. And now we have because the group is assumed to be residually finite, so you can fix a sequence of finite index normal subgroups where has a trivial intersection. Now you equip this gamma with the metric respect to S, the finite generating sets, and give the quotient, this finite quotient group with the quotient metric. Then we say that this sequence of finite groups is a sequence of finite vertex transitive graphs. and we call it bulk space of gamma with respect to gamma n. And as I mentioned, Margulis had the construction of expanders. In fact, he used these bulk spaces. So he proved is that if gamma has a property T, then he can show that bulk space are expanders. Basically, he using the fact that the property T means that all the unit representation is isolated or spectral gap, something like this. To prove this, in general, you can show that the bulk space is expander if only the group has a property tau with respect to this family. So this is a weaker condition. Property tau is weaker than property T. So this tells you that you don't have to look at all the presentation, but look at the presentation you needed. Exactly the quasi-regular presentation from the final quotient onto the Hilbert space. Anyway, this is not the main point. The main point is that we know exactly when the bulk space is expanders. Okay, so if we only look at the final, look at a sequence of final vertex transitive graphs, for instance, bulk spaces, then the degree or valency is uniformly bounded with increasing cardinality. Then we can show that the string condition are equivalent. Xn is an asymptotic expander, and Xn are expander, and the average projection inside the uniform row algebra. So I mentioned before that the P inside uniform row algebra doesn't imply this expander, for instance, this perturbed expander, because the perturbed expander is not the vertex transitive graphs. But once we restrict our attention to a nice graphs, then we can conclude the expander. So this is not completely wrong to say P is inside uniform row algebra, then the Xn are expanders. In particular, for bulk space, we have this equivalence. Okay, is any question so far? Okay, then I will go to my last slide. Let me see, how many minutes left? How much time left?
You have, let's say, 10 more minutes if you want.
10 more minutes, okay. Then I can go a little bit slowly. So now I want to talk about a generalization called the measured asymptotic expanders. Okay, so this is a joint work with Specula and John, and then we develop something called measured asymptotic expanders. What that means? I don't know. In the beginning, we talk about the expander or asymptotic expander. You can see here. Everything we look at is look at the cardinality of the states, the cardinality of the boundary. So you should think about the cardinality is the counting measure. So now you just change the counting measure by any probability measure on Xn. So if you have so if you have a sequence of Xn finite metric spaces, then you equip the probability measure mu1 on each Xn. Okay, so then you can define this exactly the same way, just change the counting measure by mu1. So that is the differences. So only difference is that you can also think about you change uniform measure by some non-uniform measure. Then, okay, so what we can prove is that using this notion, we prove that if we have a block rank 1 cost projection on a sparsal space belongs to uniform row algebra, if only if X is a measured asymptotic expander. Before we prove that the average projection belongs to this algebra, if only if X is an asymptotic expander. So asymptotic expander means it's a measured asymptotic expander with respect to the counting measure. Okay, so what is block rank 1 ghost projection means? So this is a projection which is a block diagonal, and each block is a rank 1 projection. And if you have rank 1 projection, of course you can find the unit vector on your Hilbert space, which is associated to this projection. Then you take a square, then this square is exactly the measure mu1. So that's why we have this mu1. So for each such projection, we get a measure, and then we show that this projection inside uniform row algebra is that this with this measure, this given measure is a measure asymptotic expander. So you have to make this correspondence precise. So for instance, average projection is one of the examples. So that is a block diagonal projection, and is each block is a rank 1 projection, and the associated measure is exactly the counting measure. So that is what we proved. So you may think about this proof should be very easy, like just replace absolute value by the counting measure by this mu_n. Yes, in fact, in most of the cases, everything is just do like this. But there one difficult part, which makes this is very difficult, take me so long time, is that can you remember that we proved that the expander implies the average projection inside uniform row algebra. We have to look at the Laplacian operator. We state that the zero vector is exactly, the zero eigenvector is exactly the constant function. So here we're using something from the random walks. Then we always have random walks here because we look at the counting measure. But here we don't have that fact because we look at all the rank 1 projection. So we get all the kind of measures. You cannot expect every measure has a random walks or given random walks. So what we do is that we given such mu_n, we construct another measure mu_n prime where has a random walk, inversible random walk, such that the mu_n and the mu_n prime can control each other. So then you use the mu_n prime with the has a random walk, do the same proof as the counting measure case. Then you just go asymptotically to get the fact you wanted. So what I say is that then we can prove, for instance, we can define the measure expander. Then you show measure expander, the corresponding average projections belong to uniform row algebra. Then you go to the limit. Then you can show general block rank 1 coarse projection inside uniform row algebra. Okay, I do not go to the details, a little bit involved for this part. And this is the only difficult part. Okay, so there are two consequences. One trivial consequence is that we find a new counterexample to Correspondcon. So first, the new means is not expander. Another new is that the measure is not counting measure. Okay, this is the easy consequence, but this is not our main consequences. The main consequences is that we want to deal with the rigidity problem for the uniform row algebra. So what is about? If you take a two space X and Y, metric space with bounded geometry, if they are coarse equivalent, then you can show the uniform row algebra of X and the uniform row algebra of Y. They are stably isomorphic in the sense that when you tensor with the compact, they are star isomorphic. So this is always the case. So rigidity problem is ask a converse. If we know these two algebra are star isomorphic up to tensor with the compact, can you conclude X and Y are coarse equivalent? So this problem is well studied. I mean, go back to Yang and the Rufus paper and so on. Also Elias and Blaga's paper. So there are many people working on that. Then we, using our new concept measure asymptotic expander, we could conclude that the rigidity holds if either X or Y does not contain any measure asymptotic expander. So what we prove is a negation. If the rigidity fail, then one of the spaces contains measure asymptotic expander. So how we do that? This have using a fact by a nice observation. Also go back to Yang and Rufus, then generalized by Elias and Blaga, that if rigidity fails, then you can find either X or Y. Either X or Y contains a sparse subspace. Okay, then this sparse subspace contain there's uniform row algebra contains the block rank 1 ghost projection. Now then we can using our main theorem, this block rank 1 ghost projection corresponding to a measure asymptotic expander. Then that's why we prove that either X or Y contains a measure asymptotic expander. So this is a strategy. And then So this in particular proves that if either x and y are coarse embedding to LP space, then we have rigidity. Even don't have to be, they have many spaces which is not LP embedding, but still doesn't contain mesh asymptotic expander. For instance, you can write as a sequence of a quotient of finite groups by who? I forgot. Then you can find they can construct some using something called the electric expander. They can construct some space which is not contains mesh asymptotic expander, but not LP coarse embedding. So even for non-LP embedding spaces, we have a rigidity. Okay, I think I want to stop here, and thank you for your attention.
Thanks for the talk, Kang.
Thank you.
Do you have any questions for Kang?
I guess one question, you gave the impression that there are lots more measured asymptotic expanders than there are asymptotic expanders. Where are they coming from, or what's the
so you,
one, not a normal one?
Okay, so you ask difference between asymptotic expander and the mesh asymptotic expander.
You give me an example which gives rise
if I
to...
can also add to his question.
Yeah, okay, so
if I can just add to his question, would you mind also giving the precise definition of the measured asymptotic expander?
yeah, okay. I did not write it. So you look at this this definition. So you can write xn comma mu(n), where mu(n) is a probability measure on xn. So you write everything the same. Okay, so here you write you replace cardinality of xn by mu(n) of xn and less than mu(n) of a, less than equal to mu(n) of xn divided by 2. So here you also change cardinality by mu(n) of delta n and so on. So this just change counting measure by this probability measure. So that is a definition of measured asymptotic expander. So Rufus asked whether we can get the mesh asymptotic expander, but it's not asymptotic expander. In fact, we proved here that if we have this strong ergodic action on a dynamic system, in fact, we proved that the corresponding graphs is a measured asymptotic expander. So in fact, this is a one-to-one correspondence between asymptotic expander, between the measured asymptotic expander and the strongly ergodic actions. And then you have to provide extra condition to go from measured asymptotic expander to the asymptotic expander. So it's like a bounded ratio. So it's like the cardinality and the measure, they are close to each other, something like this. But now you ask me some concrete examples of mesh asymptotic expander, but not asymptotic expander.
Well, that's okay. It's,
I did not have a concrete one. I cannot write down mu(n) have one. I think Zhao Wenjiang told me he can write down one of the examples. So I did not have any measure mu(n) such as to make xn to be a measure asymptotic expander, but with the counting measure is not one, not asymptotic expander. But they should have a lot of it because you can always give a probability measure on xn in any way. You easily to find one. I think probably you just use a Dirac measure, something like that. But I do not have a good example. No, not top of my head. Yeah.
I guess one more question. Sorry.
Yeah.
I can stop it if people have questions. If X is a group, finitely generated group, say, and it contains, are there groups that contain measured asymptotic expanders, but not containing expanders? Or in that situation, if X has a lot of structure, can you?
So do you ask me whether I can find a group with this property?
Well, it's not with that property. Well, if you like, that would be interesting too. But
yeah, of course, I don't know. I mean, then you have to understand the oscillators construction first.
So you have this result which says if the graphs are vertex transitive, then being an asymptotic expander is the same as being an expander. So I'm asking for something sort of related. If you have, say, a group that contains a coarsely embedded expander in its Cayley graph, sorry, a coarsely embedded asymptotic or measured asymptotic expander in its Cayley graph, does it actually have to contain an expander?
Yeah, this is a good question. But okay, so the point is that in general, we cannot change the measures. So if we have a general measure, we don't know how to change the counting measure. So for instance, if you look at this theorem, here we talk about the asymptotic expander, but we can also talk about the measure asymptotic expander, measure expander, and the corresponding block rank 1 projection. Then we don't know whether this is correct, because the point is that because here the measure is a uniform measure, and for general is not. Then we don't know how to generalize this fact. This is the first differences. We don't know. Another one is that are we guess something like that should be true, but you have to put the correct restriction.
Yeah.
For instance, the action. Sorry.
Just curious.
No. No, it's okay. It's okay. So for instance, here the group action doesn't change the cardinality, but in the general measures, if you translate, the measure can change. So this is the one differences. Yeah. I don't know exactly, but I think something like that should be possible. Yeah.
Okay.
Yeah.
I have actually.
No, but what we.
Sorry.
Yes, of course. Let me say one more thing. I mean, what I'm interested is that I don't want to go to, so I want to go to, because now we work on block rank 1 projection. So we want to look at a block rank n projection or even high dimensional projection. So that is our focus right now. So for your question, I didn't really spend a lot of time right now. Okay, please, Braga.
You actually just mentioned what I wanted to ask. What was about the one?
Okay.
I wanted to know what you can say about block rank n, or maybe not with an n fixed, but well, they are all finite, right? Because they are in the xn's, but anyway.
Oh yeah. I mean, so far we do not get any good progress, but what we think is that maybe there is something to do with like a high dimensional expander, something like this. But we cannot find out the correct definition in this moment. Even for rank 2, we don't know how to do that. So the point is that if we know there are two rank 1 projection, if we know sum of these two projection inside uniform row algebra, we cannot say anything about each of them, whether they're inside the uniform row algebra. So this is the difficulty. One of the difficulty, yeah. And if we have,
I don't know if it's easy to point out exactly where this rank 1 plays a big role or not. Maybe it's too technical in the proof, but when you're going from
it really play a big role, yeah.
So, but I don't know if it's easy for you to point it out for us now, where actually the 1 is being used. If it's not hard,
this is really important. Yeah, is really crucial. If it's rank 2 has 2 vectors or 2 measures or whatever, then everything's broken. At least not for this proof. far from correct. Probably you need new ideas how to deal with that. How can I explain?
As I remember, the measure is coming directly. The measure is just the vector which it's projecting onto. So your sequence of measures from your paper, right?
Yeah.
So
yeah.
the measure comes directly from the projection, and then there's no obvious choice anymore.
Yeah. In fact, okay. So in fact, we have to say more about the rank 1. In fact, is corresponding to a L2 vectors. So then you take a square. Then that is our probability measure mu1.
Sure.
And this is crucial. But if you rank 2, then I don't know what you get. Maybe you get 2 vectors or whatever. Then I don't know how to handle this situation so far. And but if you have rank 1, now we look at the rank 1 projection. But if you look at rank 1 positive operators, we can still able to go through, but it's just a little bit harder. So you get 2 vectors because rank 1 operator is like you give a 2 vectors. You can write in the 2 vectors, then we can still play a little bit. Then you can go through the proof. But that is the not big differences. Yeah, but we would like to go to high dimensional cases. What we can prove. For instance, maybe we can use this kind of thing to detect Correspondcon conjecture. We know that under suitable condition, if Correspondcon conjecture fails, then you can always find a non-compact ghost projection. But this projection may not be block rank 1. So that is a trouble.
Okay, well, thank you very much. Do you have any other questions for Kang?
Thank you.
I'll stop recording then.